All right. We're going to go through my 2025 practice exam in the new format for AP Physics Mechanics today. So this is supposed to give a good overview of the course content and especially the new format. So I put this blank in the description for you to work it out first for good practice. But of course, we're going to go through it right now. I'd say this is an average set, although parts of it may lean towards the easier side. But I tried to mix the whole course content in where I could. Okay, so first up, we have question 1, which is the math routines question. So this is mostly about deriving, although we'll always have some sort of a diagram to draw. So additionally, it's nice to figure out what topic each question is, because they're more compartmentalized this year. So this looks like one of the main 4 categories. It's either the forces category or the rotation category. And I actually see it as rotation, 1, because I wrote it, and 2, because my pulley has mass. So in this diagram, we have a pulley that has mass connected to 2 blocks. So it's this sort of modified Atwood setup. And we have a block that's going to be released from rest and strike the ground. So our first question asks us to find a sort of energy bar chart for each of the 3 masses in the system. So it says that as the crate falls, its change in GPE is E, and we want to figure out how the kinetic energy right before the block strikes the ground will compare between the falling crate, the table crate, and the pulley. So again, this is a rotation question, so we can't neglect the contribution of the pulley because it does have mass, even though there is no slipping. And we're actually going to apply the no-slip condition right away here, because we're given that the string does not slip during this process, which guarantees that everything in this system is accelerating at the same rate, which means that it's also moving at the same linear velocity, at least at the edge of the pulley. And we'll apply that relationship with omega and v later. So we'll just start with our expressions for kinetic energy and see what we can learn. Because we haven't derived anything yet, so this is a mostly qualitative problem. I didn't actually tell you to label numeric values, so it's not required. So for the falling crate, I know my KE is just 1/2 mv squared at the end. My crate on the table is also going to share that speed, except it has a mass 3m, so we can already see an increase in kinetic energy between the table crate and the falling crate. And then the pulley, well, its relevant energy expression is 1/2 times I times omega squared. So I can't really compare with that right now, but luckily I was given that the rotational inertia of the pulley is 2 mr squared. And then due to the no-slip condition, I can say that omega is just v divided by r. So now we actually get a more usable expression of 1/2 times 2m times vf squared. And now I can directly compare these. So ignoring the 1/2s, because that's the same everywhere, I effectively have an mv squared over here, a 3mv squared over here, and a 2mv squared over here. So we can actually see it's going to split into sixths, where we have 1/6, 3/6, and 2/6, respectively. So for my bar chart, I see these are split by thirds. So my falling crate has 1/2 of a third of energy. My pulley has 1/3 of the initial starting energy. And my crate on the table has the remaining 1/2. So that might be something closer to this. All right, so if we actually wanted to label these with numeric values, I would call this 1/6 of the energy that we started with. I would call this 1/2 of the energy that we started with. And I would call this 1/3 of the energy we started with. So here's how we'd actually score it, because we didn't have to go this in depth, because it's just a qualitative part. So first, I would give you a point for the correct ranking of energies. So if you said that K of the falling crate was less than k of the pulley, which was less than k of the table crate. And you could figure this out by using the moment of inertia coefficient as a sort of effective mass. Because they're all moving with the same speed, you can just rank their kinetic energies by ranking the mass. Then you get a point for your sum of the kinetic energies to approximately equal the starting energy. So it looks like roughly all the bars work out to the initial. Because if your GPE went down by E, well, all of your kinetics combined have to equal that. Because it's all that gravitational potential energy that's split between the three objects. So there's your 2 points there. Now the rest of it is derivation points. So now we're on to the derivation. So here it's just going to be one part for the A derivation. So a 5-point derivation for finding the magnitude of the total angular impulse that is delivered to the pulley about its center of mass as the hanging crate falls. So you're going to answer in terms of m, r, and physical constants. So to begin, angular impulse is a bit of a weird thing to solve for. So let's remember that linear impulse, or just impulse, is defined as delta p. And it's probably most helpful just to think of the m delta v way of finding impulse. There is a force times time one, but it seems like time is going to be a thing we don't want to solve for in this problem. So we're going to compare this to its rotational analog. So angular impulse, which I usually denote with a little theta, is the change in angular momentum, and I delta omega seems to be the best one that we'd use here. So all we have to do is find the omega change of the pulley, because we know it's moment of inertia. So based on our diagram in this part, it seems like energy is a very nice solution to get us there. If you use Newton's laws and kinematics, that is a full credit solution. It's just not going to be the one I show. So if you want to do this by finding the net torque on the pulley and finding alpha or A for the system, then some kinematic stuff, you will get the correct answer. I'm just doing it with energy because I think it's a bit more elegant. And the diagram helped us think about it. So I'm going to start from first principles again. We actually did a lot of the heavy lifting in the bar chart already, but I'm going to use the fact that the initial GPE of the system is equal to the final kinetic energy. So my initial gravitational potential energy is going to be mg times h, which is 9r, because that's how far the block fell. And then for my final kinetic, I actually have 3 different objects to consider. So I have the falling crate, 1/2 mv squared. I have the table crate, 1/2 times 3 mv squared. And then I have the rotating pulley, 1/2 I omega squared. Of course, we eliminated this earlier, but we're just going to rederive that. So I'm just going to solve for v first, even though omega is probably better to solve for directly. I'd get 9 mgr is equal to 1/2 mv squared plus 3/2 mv squared plus 1/2 times, well, the rotational inertia of the pulley was 2mr squared, and then omega is v over r, so I can write omega squared as v squared over r squared. And now we can start to do some combining. So we get 9 mgr is equal to 1/2 mv squared plus 3/2 mv squared plus 1. The r's actually cancel, so I just get 1 mv squared. And notice that's our sort of energy splitting into sixths that we saw in the bar chart. So I get 9 mgr is equal to 1/2 plus 3/2 is 4/2, or 2, plus 1 is 3. So I get 3 mvf squared. And now we can cancel that m that we've been looking to get rid of, and we get that the final linear velocity is square root of 3gr. But more importantly, We actually want omega because we're dealing with the angular aspect. So omega is just going to be that divided by r. Then we just plug in because we said the angular impulse is just going to be delta L, which is equal to I times delta omega, which is 2mr squared times square root of 3gr divided by r. And that's our final answer. Of course, you could simplify it, but I'd rather not. So anything equivalent to that. So this is a 5-point derivation in problem A. And here's how I would award points for an energy solution. So first, I would award a solution for a multi-step derivation using energy. I would then give a point for a correct energy expression that relates to all three masses. I would give a point for applying the no-slip condition. I would give a point for a correct computation of V or omega, and then I'd give a point for a consistent substitution into an expression for angular momentum. If you were to do this with forces, I would probably give a point for starting with Newton's second law. I'd probably give a point for the acceleration. I'd give a point for the no-slip condition somewhere in there. I'd give a point for V and a point for the substitution. Now, part B. This part of the MR is always a same topic, but just entirely unrelated, or at least a good part B should be. In a different scenario, the pulley is replaced by a disk of rotational inertia I about its center. We're applying a torque T0 about to the edge of the disk, causing it to rotate. But as it rotates, there's some sort of friction, and the faster the disk rotates, the more that frictional torque actually fights the motion. So picture it like the higher rate that the disk rotates, the more it's sort of dragging against that surface. And we want to use integral calculus to derive an expression to show that we get this nasty function of omega versus t. But if you've taken E&M, this looks very capacitor-esque. I call this the exponential approach equation. Or if you've taken physics C, just in general, you might know this as like a drag type equation. So first, if I want omega and I'm only given stuff about torque, I really should be thinking something like the net torque is equal to the moment of inertia times alpha. Right, just Newton's second law for rotation. So helping my rotation, I have a torque T0, but fighting my rotation, I have a resistive torque C times omega. And then I also know that alpha is the rate at which omega is changing. So now, this turns into a differential equation I want to solve. So rearranging variables, I would get d omega divided by T0 minus C times omega is equal to 1 over I times dt. And now we have a separated differential equation, so we're just going to integrate. So I get d omega divided by tau 0 minus c omega is equal to 1 over I times dt. So now for my integral, the t side is easy because I just start from 0 and I end at t. And then for my omega side, well, it's actually still pretty simple because it starts from rest, 0 for the angular speed, and it ends at some angular speed omega that we wish to find. So now we go through. This is always going to be some natural log situation when you have a denominator. So applying the chain rule, you get the natural log of the inside. I'm not doing an absolute value because we're never going to have domain issues, evaluated from 0 to omega. But we can't forget about the chain rule inside. So the chain rule, just like it's multiplying for differentiation, it's dividing for integration. So I have to attach the reciprocal of the coefficient to omega. And then if I integrate from 0 to t of dt, well, that's just t. So the right side's actually done in terms of the calculus. So now we just got to plug in. I'm going to give myself some more space here. So now we get negative 1 over c times ln of, well, if you subtract 2 logs, that's the same thing as dividing the insides. So plugging in omega as my numerator, I would get t0 minus c times omega, and plugging in 0 for omega gives me t0 minus 0 as the denominator. Then let's move the coefficient to the other side and simplify the log. So I get ln of t0 minus c omega divided by tau naught is equal to negative ct over I. So it's starting to come together because I can see my exponent now will match. Now I'm going to exponentiate both sides, and I'd get t tau 0 minus c omega over t0 equals e to the minus ct over I. Simplifying the fraction, I'd get 1 minus c over tau naught omega is equal to e to the minus ct over I. So then I would get 1 minus e to the minus ct over I is equal to c over tau naught times omega. So thus, omega is equal to tau naught divided by c times 1 minus e to the minus ct over I. So I'm almost certain you will have some sort of differential equation with similar steps to this to solve on the actual exam. This one was unfun because it wasn't just a decaying exponential, it was that sort of approaching a terminal value, which makes sense, because as your disk spins and spins and spins, the rotation rate is going to cause extra friction. So there's this spot where the rotation becomes too fast to actually allow it to accelerate anymore. So notice we got tau naught over c as our factor, and then our exponent was negative ct divided by I. And that's exactly what we want here. So this is actually only worth 3. So first, your first point would be an appropriate multi-step derivation starting from Newton's second law for rotation. Your next point would be for a valid separation of variables / integrating with correct limits, and all that algebra is your third point. So simplifying all that down to this is your third point. So it becomes a bit tricky to figure out exactly how it's graded in terms of jumping from the integral to the answer, but generally, if you've plugged in something that's algebraically equivalent, just showing that simplifying should be good. So again, the MR question is out of 10. So it's 2 for the diagram, 5 for the big derivation, 3 for the little derivation, even though the little derivation actually took us way longer time because it was that diff EQ. All right, now on to the long question, the translation between representations. So we have instant thoughts of some sort of momentum idea happening here because I see 2 things about to hit each other. So the diagram in figure 1 shows 2 blocks at time t equals 0. We have a block of mass 2m moving at v0 towards a stationary block. At time t1, they collide, and there's this variable force versus time function that looks quite nasty that shows the force acting between the blocks on that interval. And it does tell us immediately after the collision, both blocks are moving to the right on a friction-filled surface, and the block of mass little m comes to a stop at time t equals t3. So the TBR question is worth 12 points because it has you do a whole bunch of different skills. And the first of which is drawing a diagram of representation. So on the diagram below, draw a qualitatively accurate diagram showing the relative momenta of each block before the collision and the relative magnitudes of the impulses during the collision. So what we have first is immediately before the collision. So before the collision, clearly one block is moving and the other isn't. So this should be an easy diagram to fill out. Before the collision, we have a block of mass 2m. So I'm just going to give it a lot of momentum. I don't know why I insist on doing the coloring of the bars. We're not going to do that. And then for my block of mass m, I'm going to put 0. Now, during the collision, we know that by Newton's third law, the force exerted on each object is equal and opposite. So as such, in any collision between two objects, they're going to have equal and opposite impulses. And we don't need to know how tall these bars are for this part, but we do know that no matter what I'm drawing, since it's just the magnitude, I'm going to make them the same height. So this is out of 3. And how you get your points here is you get your first point by just getting the left diagram. So P of 2m is not 0. P of m is 0. Then you get another point for showing that both impulses are not 0. And then you get another point by saying that the impulses are exactly equal to each other in magnitude. And actually, since you know that both blocks still move to the right, you actually know that it's also less than the initial P0 of the system. So you also have to make sure that your diagrams are less than the total momentum of the system initially. Although I don't know if that's in the rubric or not. Wait till I post that. So that's how you get your 3 there. Then derive an expression for the distance d traveled along the rough surface by the block of mass 1m before coming to a stop. So after they collide, we want to know how far this block travels. So this is a pretty straightforward kinematics question. So we know that as the block is on the surface with friction, so as it's on the part that actually has friction on it, we know that the force is acting on the block. It's a pretty standard situation where we have the normal force and gravity that are going to balance. And then we have this sort of net frictional force that's applying that acceleration. So we know that the net force acting on the block is just going to be equal to, with a negative sign, that frictional force, which is just negative mu times the normal force, which by balancing is mg. So as a result, we know that the acceleration of the block, after applying Newton's second law, is just going to be negative mu times g. So that's definitely a key part of this problem, is figuring out this acceleration. There is an energy approach as well, if you want to apply work energy theorem to this. So we're really close. We can just apply kinematics, and the relationship, since there's no time here explicitly about how long it takes, or there is, but we can't use it, we're going to use the fact that we're going to use the relevant kinematics equation, v1f squared equals v10 squared minus 2ad. And solving this, we'd get 0 squared equals v10 squared minus 2 times times mu g times d, which would tell us that the distance d is just equal to the initial speed of the block divided by 2 mu g. So what is that speed? Well, we have to apply momentum conservation to do that, or the impulse momentum theorem. So we know that this block is initially at rest. So we're going to use the fact that delta p is going to be equal to the integral of f of t dt. So applying this for block 1, It says the blocks collide on this interval t1 to t2, and we have this nasty impulse, or we have this nasty force function that looks like this. But it's actually not that bad because there's only one thing that's a variable, and that's that quantity t minus t1. So simplifying, we can pull everything out of the integral. That entire first term can come out. And then just using the chain rule on this, the antiderivative of this expression is t minus t1 quantity squared divided by 2. And we're evaluating from t1 to t2. So that actually makes our life really nice, because when plugging in at t1, we get 0. And when plugging in at t2, we get the difference of time term to actually cancel out. So we actually just get mv0 as our impulse. So now we can apply that. We can use the fact that m times v1 minus 0, because m delta v equals delta p, is equal to the impulse of mv0. And well, that just tells us that v1, the speed after the collision of block 1, is simply v0. And then that allows us to go back into our expression for d and just plug in v0 in there. So d is just v0 squared divided by 2 mu g d. Sorry, 2 mu g. And that's our answer. So let's look at our point distribution, because this one is out of 4. So first, you get a point for any multi-step derivation that uses kinematics / energy to solve for d. Then you get an expression for a correct expression for d in terms of the velocity of the block after the collision. You get 1 point for attempting to use impulse momentum theorem to find the velocity of the block, and you get 1 point for a correct impulse that is substituted into your expression for d. So there's your 4 points. So anything with energy / kinematics, a consistent answer for d, impulse momentum theorem, and a correct impulse, or sorry, a correct v0, that's plugged in. So now you have to graph a sketch of velocity. So the TBR also has a graph portion. So we want to graph each block. So first, we'll actually kind of do these in parallel. So the heavier block, the one that's initially moving, it does tell us to label some velocity at t2. So at v0, my block of 2m moves towards the stationary block of mass m. Then during the collision, we know that the block with mass 1m experiences this force that actually increases with time to a speed of v0. So I do know segment-wise, I'm going up here. I'm going to make it concave up. And then after that, the block slows down due to the friction surface, and that's going to be a constant force, so that hits T3 in a linear fashion. And then to do that over here, we should figure out where the velocity is going to go. So I do know that the momentum change is the same, because it's the same force. But if I apply the same force to a heavier object, it's going to change its speed less. And if the 1m block went from 0 to v0, well, an object with twice the mass must only have half the speed change. So I'm still going to draw that concave up graph, but I'm going to stop it at v0 over 2. And then this decreases actually with the same slope as the other graph, but it's just going to hit before T3, because if it's also hitting that surface at the same time, It has the same acceleration because it didn't depend on mass, but it just had a less starting speed. So it's going to actually take half the time to stop. But that won't be one of the points that's graded. So your first point on this is going to be the correct behavior of both graphs from 0 to t to t1. So that means your 2m graph starts at v0 and is constant, and your m graph starts at 0 and is constant. Then you get another point for the region between t1, t, and t2 for each graph, including the intercept. So you need a consistent intercept, meaning momentum is conserved. So if you had a wrong answer for one of your graphs, as long as momentum was conserved, your intercepts might not be the same. So if your M graph didn't go up to V0, you might have a different setup. So your intercept just has to obey momentum conservation. And then 1 point for the M graph sort of linear decrease. And it wasn't really clear what was going on with the first block, so nothing past T2 is actually graded on the 2M block. So there's your 3 points there. And it's also not, we're also not grading on concavity for the T1 to T2 portion, just something that non-linearly increases for V0 for the M graph and non-linearly decreases for the 2M graph. Again, check the rubric for a description on that. Indicate whether your graph is consistent with the impulse diagram. Well, given that I referenced it in doing C, you bet it's consistent. But really all that's saying is these two objects experience the same impulse, but due to the difference in mass, they did not experience the same velocity change. So yes, the two representations are consistent. As shown by the graphs, the 2m block changes speed from v to v over 2, while the 1m block changes speed from 0 to v0. The two blocks have equal impulses, but in opposite directions. Even though the blocks have the same momentum change, as shown in the diagrams, the speed change is exactly half on the 1m block. So I should reference that this comes from the chart. So I'll say this is from part A. So that's how you get your consistency point. So again, if it's inconsistent, you have to say that and justify it. So it's kind of hard because there's so many answers here. You get one for the claim and one for the justification. So if they are inconsistent, you can earn both points. All right. Now, on to the lab question. So, experiment 1, students are tasked with calculating the mass of a hooked metal ball that's shown above. The students do not have access to a scalar timer, but instead are given a ruler and a large number of identical springs whose constant you know. So first we'll describe a procedure for collecting data that you can use to calculate the mass of this ball. So given the fact that it's a hooked mass and springs, we know this is a Hooke's law extension sort of thing. So the key here is to just, yes, we're going to hang the block by the spring, but what we're going to do, because we have multiple springs and we want to get multiple data points, is actually start hanging these springs in parallel and suspending the ball from multiple of these springs at once in parallel, because spring constants just add in parallel. So essentially that's my procedure. I could imagine there's others that are out there that are also valid. Just assume this was the intended solution. So this part is out of 2. You'll get, again, if you have a totally different experiment than this that uses its equipment, it could very well be fine. Every time I ask a lab question, I find a procedure I wasn't expecting that's totally valid, so that could be you. Attach a spring to a ring stand, place the ball at rest on one of the springs, record change in length to reduce uncertainty, perform multiple trials, record the extension versus number of springs used. So you get 1 point for anything about hanging the ball from the spring or measuring extension using that. So make sure that you don't just say length of the spring, something about extension, because that's really relevant here. And then another point about varying the same procedure for multiple springs, whatever it is. Again, I'm not totally sure how you do this with one spring. Let me know if you have your own procedure that you think of there. Describe how the data could be graphed and how you could graph it. Well, if the forces balance, we know that the weight is balanced by the spring force. So my mg is equal to the total spring constant times the extension. And in parallel, spring constants add, just like like capacitors, not like resistors. So I varied the number of springs. So if I have two springs in parallel, it's essentially a spring of constant 2k. So this gives me mg is equal to n times k times delta x. So I have n and delta x. So I'm going to divide both sides by n, and I would get mg over n is equal to k delta x. So I would say graph k delta x versus g over n, and then my slope is equal to the mass. Because again, all I'm doing is I just did a clever grouping of my variables. So I said this is y, my k delta x, and this is x, this g divided by n. Of course, there's other ways. Like I could just say graph delta x and 1 over n and deal with your slope algebra that way. But if the formula is not too bad, I like to just make the slope the answer. So here's how you get your 2 points. So you get 2 points, one for a valid relationship and one for a valid way to solve from that relationship. So here, k delta x versus g over n will actually yield a straight line. So that's how I got the first point. And my second was telling that the slope of the k delta x versus g over n graph is just the mass. So you could also just say the slope is equal to this fraction and solve for m. You don't really have to solve it if there's a bunch of garbage in your slope. So there's your 2 there. Next, experiment 2, students want to calculate the mass of a different ball. So for whatever reason, in question 3, all of these students are very interested in finding the mass of balls. Do with that information what you wish. One student twirls the ball in a horizontal circle of radius 0.1 meters above their head and records the magnitude of tension in the string using a wireless force sensor. So they're just spinning a ball on a rope above their head in a horizontal circle so we can neglect gravitational effects. And we're just figuring out the tension in the string, so there's some force sensor attached. And then in each trial, they actually just record the amount of time t it takes the ball to spin around. Using video software, I presume, because this would be very hard to do live. And the circle radius is actually kept constant here. So we want to figure out how we solve for m. So if you see this diagram and it's about forces and strings and circles, hopefully our mind went to the fact that centripetal force, or a force that causes you to go in a circle, can be expressed as mv squared over r. Unfortunately, we didn't have v, so we're going to have to substitute away for it. So they're twirling it at constant speed. We can make that assumption because we're looking at the average force on this sensor. So the force is m divided by r times the speed v. And v is nothing but distance divided by time. And in our case, the radius of the circle is L, and the distance traveled in one cycle is 2 pi L. So we get the relationship force is equal to mass times 4 pi squared L divided by T after simplifying everything. So this time, because I actually just did it in one shot with the slope in my own experiment, I'll show you how to do algebra with the slope this time. So I'm actually just going to take the force as one of my variables and 1 over t squared as the other. And notice that m, 4, pi, and l are constants. So on my horizontal axis, I am going to put the force, and on my vertical axis, I'm going to place vertical axis, I'm going to do the force, and on the horizontal, I'm doing 1 over t squared. I have to be careful with my own wording here of what I put where. So you get 1 point here if you graph something with the same functional dependence as this. So f versus 1 over t squared works. So anything that's equivalent to that. So you could do this with all your constants lumped in as well. If I were actually doing this, like personally, or when I did this to check, I graphed f versus 4 pi squared L divided by t squared, so my slope is just the answer. Now we're going to transition to Desmos, because I just want to show you how to do this live. So we'll do that. All right. Now we're going to show how to actually analyze this data here in Desmos, because we do have to transform it. So first of all, I always like to rename my columns of my original data set to what it was. So first, this was time, capital T, and my x, and my y was the force F. So I just do that quick renaming. Make sure to keep the subscript 1 so Desmos knows it's a table. And if we were to click the magnifying glass right here, we see that, yeah, this is definitely not a linear data set. But we said something that you could graph to get a linear data set was the force as a function of 1 over t squared. So just so you know, I'm going to type my transformed variable y as it's just going to be force. So I am just graphing the force as my new y. And then my new x variable is going to be 1 divided by t1 squared. So now I'm actually just going to get rid of that old table because I don't need it. I'm going to stop graphing from there, and I'm just going to graph a new table. And I'm going to graph my transformed x and my transformed y. So make sure to keep it like x then y so you don't accidentally flip your slope. So if I graph this data set and use the magnifying glass, well, look at that. It's quite linear now. So then you just click the regression button, and it does a linear regression. So I see that my slope, which is the thing I'm interested in the most here, is equal to 0.161 approximately. And you could even copy paste it down here if you wanted that equation for future use. So we can use this fact that our slope is going to be this 0.161 when we need it. We'll make sure to reference this when we actually solve it algebraically. All right. So now that we successfully transformed our data using Desmos, what we can do now is actually transfer that to the paper. So I made my 1 over t squared column here, and I went through and actually plotted my points. So I don't want to gloss over this because this is where we should absolutely earn our points. No matter what you graphed, whether it's correct or not, you can earn all 3 graph points here. So this is out of 3. You get 1 for your axes. So you scale it properly and you use correct units. Do not forget the units. You get 1 point for plotting the points. And then you get 1 point for drawing an appropriate best fit line. So I actually saved that for doing it right now because I just want to give some tips there. So the best fit line is the line that approximates the trend of the data the best. So I'd say this is pretty decent. Again, your goal is to try to get like half above and half below the line, but that's definitely good enough. And don't force it to the origin. Definitely looks like my line's not going to the origin. So I thought that's a pretty decent best fit line. So that gets you all 3 points, regardless of what you graphed was right or not. So even if you just said F and T, which is definitely not a straight line, you'd still get your 3 points if you graphed it properly. Just be careful on how you're drawing that fit line. So using the best fit line, along with our given value of the length of the string, calculate M. So our formula says that the force is equal to M times 4 pi squared times L divided by T squared. And as a result, this means that we could write F is equal to 4 pi squared L times M times 1 over T squared. So as a result, if we graphed F versus 1 over T squared, the slope would be equal to 4 pi squared L times M. So then if we were to solve this for M, which is what we wanted, I should make it capital, but it's too late now. I would solve for M and say that it is my slope divided by 4 pi squared times L. And we should indicate if our slope is coming from Desmos. I always encourage you to actually use regression for the slope. It's much easier to just make mistakes if you're doing rise over run. So here, my slope would be approximately 0.161 from Desmos divided by 4 times pi squared times L, which was 0.1. And to make sure I don't miss out on a potential point, I'm going to say that this came from Desmos. Even better would be to write your best fit equation. And doing this, you'll get that your slope, or your M value here, is approximately 0.04 kilograms. So that is our answer. So now for the points, you get 1 point for correctly relating the slope to the equation F equals 4 pi squared ml over t squared. Pretty hard if you didn't get that equation to get either point. And then you got your second point for an approximately correct value of 0.04 kilograms. So there's that point. All right. Now, we're going to go in and do our last question. Again, lab questions worth 10 also. So 2 for designing your experiment, 2 for analyzing it, 1 for the correct graph relationship, 3 for a consistent graph and best fit line, and 2 for the analysis. And lastly, we got the QQT. So this one is actually about gravitation, which is interesting because there's not many about it that are on the free response portion. So we have a space probe of mass little m is exploring 2 spherically symmetric planets of radius big R and the same total mass that are very far apart. So same mass, same radius. Planet A has uniform density, while planet B has density that increases with the distance r from the center of the planet via this relationship where the density of planet B increases from the center. So that's the main part here. On each planet, the probe is dropped from the surface into a narrow tunnel and falls to the planet's center under the sole influence of each planet's gravity. Each planet has no atmosphere, so we can ignore any sort of friction happening with the air as it falls into the tunnel. So first thing we want is let TA and TB represent the time required for each probe to reach the center of the planet. Compare these times and justify without math. So Uh, the thing that's actually accelerating these probes is the mass that it feels below it. So it's all about the enclosed mass. And actually, as we see here, if planet B has all of its mass sort of distributed uh, higher in the planet or further out, as you fall in the planet, you're actually going to feel less and less of it. Because Newton's shell theorem says that you actually don't feel any of the effects of the mass that's above you. You don't, because different aspects of the shell will cancel. So if planet B has its mass further from the center, well, that means that you're not going to experience that mass actually pulling on you. So you're going to accelerate less in planet B. So it's going to take you more time to reach the center. So let's break that argument down. The gravitational field depends on the enclosed mass at a given distance from the center. In planet B, more of the planet's mass is distributed towards the outer layers. There's a weaker gravitational field inside planet B, and as a result, the probe in planet B will experience a lower acceleration, so it'll take longer to get to the center. So if instead all of your mass was actually at the center, then the time would be less. But so I think that's actually a good sort of extreme case to look at. So how would it look if all your mass was towards the center? So it was basically hollow. Well, of course, it's going to take a lot less time in that case if your planet was just a point mass. But here, your mass is further out, so it doesn't have that effect of pulling you. So this is out of 3. So checkbox is 1 point, and then you can earn your 2 justification points independently, as long as you said 1. Anything relating the gravitational field to the enclosed mass, and then for stating that more of planet B's mass is distributed towards the outside, leading to a weaker field inside planet B. So you have to say B has a weaker field, and you have to relate that to the gravity in the enclosed mass in the planet. So now we're going to derive an expression for TA. Luckily, that's the one. I don't really know if we actually can find an expression for TB. I haven't thought about it too hard. But something really nice happens that makes TA actually possible to calculate. And interestingly, the expression TA apparently can only be written in terms of rho A. So we want the time it takes to reach the center of the uniform mass density planet. So what we know is that by applying Newton's law of gravitation, we once again know that the net force acting on an object, in this case, is going to equal the gravitational force. So the acceleration of our space probe is going to be equal to the gravitational force gmm over r squared, where the big M is actually the enclosed mass that we sort of see below us at any point. So as a function of how far you are from the center of the planet, we get this expression. So we see that the mass does cancel out, so the acceleration is equal to big G times the enclosed mass divided by r squared. But due to the fact that we have uniform density, if we're a distance r from the center, well, we're just enclosing mass that's equal to density times volume. And our density is just rho A, and the volume of a sphere is 4/3 times pi times r cubed. And again, we're using this little r because as we move further, the enclosed mass is going to vary. So if you use big R, that would only be valid for outside the planet because you've used the entire masses, the entire planet's mass in that case. And we actually see 2 of the R's cancel. So we're actually left with an acceleration that's equal to 4/3 times pi times rho A times big G times R. And actually, what we see here is that our acceleration is taking the form of some constant times our displacement from the center. So this is actually a restoring force relative to the center. So we'll attach ourselves a minus sign here. Because if you're above the center, you're going to be pulled down. If you're below the center, you're going to be pulled up. So this is actually just like a spring or a pendulum. So this follows the form of simple harmonic motion, which says that A is equal to some negative constant, omega squared, times its position. So in this case, we see that our omega, our angular frequency of oscillations, is just square root of 4/3 pi rho a times g. And similarly, if we know omega, we know the period of the motion is 2 pi divided by omega. So we'd get 2 pi divided by square root 4/3 pi rho times g. But this actually represents the time it would take the probe to fall through the planet, pass through the center, pop out the other side of the planet, and come back. So actually, TA, the time we actually want to solve for, is just a quarter cycle. So that would just be pi divided by 2 square root 4/3 pi rho a g. So quite the expression. And I thought this was an application of some topics that we don't usually see together. Of course, this gravity in the planet SHM connection is something that many of you have probably seen once or twice, but this was kind of a novel problem that I thought was interesting. So first, you get a point for relating the acceleration to the enclosed mass within the planet. So a multi-step derivation that involves equating the acceleration to the enclosed mass is your first point. Then you get a point for correctly solving for the gravitational field strength inside the planet, which would be this expression. And then you get a third point for a correct final answer. Of course, I didn't simplify it. You could do a bit more with this. So now we have a different situation where after finding the required samples, the space probe leaves the surface of each planet. The minimum speeds required for the probe, starting from the surface, which is important, to reach a distance very far from the planet is VA and VB. We're basically comparing the escape velocity. Well, even though the planets do have very different densities, the second form of Newton's shell theorem says that if you are outside of a sphere, its gravity looks like a point mass. That mass is entirely centered at the center of the sphere. And since the planets have both the same mass and the same radius, if you're outside the planet, you can't tell which one's planet A and which one's planet B. So their escape velocities are actually equal, even though the g inside the planet is definitely not the same. So both planets have the same mass and radius, meaning the gravitational field outside each planet will be identical, since it's dependent on only distance and enclosed mass. Thus, the escape velocity will be the same for each planet. If you actually work it out, you'll see escape velocity is proportional to sort of the square root of the planet's mass divided by its radius, and that fraction is definitely the same because the m and r are the same. So you get 1 point. 1 point for your selection, 1 point for your answer. This time you can't get the second point if you get the checkbox wrong. So the QQT is out of 8. So 3 for the concept, 3 for the derivation, 2 for the extension / consistency check. So there's my mechanics test.